Good morning, good afternoon, and good evening. My name is Claire Herbert, and I will be speaking on behalf of the Ccadi team to present our use case showcasing our development of cloud-based tools for standardized and integrated oceanographic data access. We will use the example of calculating ocean acidification in Baffin Bay, Canada, to illustrate how standardizing and integrating disparate data sets and providing cloud-based tools can streamline and simplify data analysis for research. The Canadian Consortium for Arctic Data Interoperability, or CCADI, was established in 2015. The CCADI is a pan-Canadian collaboration between 6 universities and multiple Indigenous, governmental, and nonprofit organizations with the goal to develop an Arctic research data infrastructure. Initiatives to achieve this goal include standards and mechanism development for metadata interoperability, semantic interoperability and implementation, and streamlined data services. So why should we care about ocean acidification? Ocean acidification occurs if carbon dioxide is absorbed into the ocean due to the concentration in the atmosphere being greater than the concentration in the ocean surface. Carbon dioxide then forms carbonic acid, which lowers the pH of the water and increases the solubility of biologically important forms of calcium carbonate. Climate change is associated with current issues such as rising carbon dioxide and temperature, changing distribution of sea ice, water mixing, including increased inputs of freshwater from river runoff, and melting glaciers are causing rapid ocean acidification by reducing the amount of carbonate ions freely available to react with calcium to form calcium carbonate minerals, which are the building blocks for the shells and skeletons of many marine organisms. By measuring a variety of water quality parameters, we can calculate the saturation state for calcium carbonate minerals, or the omega value. This is used as an indicator of ocean acidification. When the omega value is greater than 1, the calcium carbonate mineral is stable. When the omega value is less than 1, water is potentially corrosive to calcium carbonate, and therefore marine life that uses calcium carbonate to create their shells or skeletons may not have enough. For example, zooplankton, invertebrates, or corals. So what are the current challenges in measuring ocean acidification? In order to collect the data we need to calculate the carbonate variables, we need to collect and recombine multiple data sets and formats produced by a variety of analytical and laboratory instruments. Instruments deployed from a ship collect both in-situ data and whole water samples that are sent to a lab for analysis. Data is provided back to the user from multiple labs and in multiple formats. It then needs to be standardized and contextual information added. Data is also hosted by different data repositories who may use different metadata standards. In addition, accessing additional contextual information, such as the amount of sea ice concentration at the sample location at the time of collection, is challenging, as this requires a user to have expertise in the additional areas of satellite imagery processing and analysis. In this use case, instrument data is hosted by the Polar Data Catalog at the University of Waterloo and is accessible via the HIRAX DAP-compliant server, where it was converted from its native format into a hierarchical format. Chemistry data is hosted by the Canadian Watershed Information Network at the University of Manitoba on an URDAP DAP-compliant server and is accessible via multiple endpoints in a variety of formats, including NetCDF and CSV. Through the CCADI, a series of common standardized vocabularies and a baseline metadata schema were agreed upon. Workflows were developed to standardize the dataset by adding the appropriate metadata and applying semantic strategies to the variable names. The schema.org metadata profile was also implemented by both repositories. Metadata standards were crosswalked to facilitate interoperability between data centers going forward. In summary, the goals of our use case are to simplify and standardize the processing and analysis of marine carbon data sets, and to develop tools to integrate additional data products such as satellite data to enable data visualization. This will allow scientists to analyze their data in ways not easily possible previously. Once the data has been standardized, it can be used for the next stage of the process, ingestion into our online cloud platform to allow researchers to calculate carbonate system variables. We used Jupyter Notebooks as the tool and converted the commonly used processing script PyCO2sys into a format that it could use. At this stage of development, we are using the EuroDataCube Jupyter Lab implementation. In the first step of the process, the two files are retrieved from their respective repositories and brought into the cloud environment. From here, the user can choose the variables from each file they want to use to create a new data product, which will be a combination of both datasets. variables that are required as input into the PyCO2 program are selected by default. The user can also select the sample depths they are interested in. In this case, we have selected data from the surface to 100 meters. Step 2 is ingesting the merged file as the input into the PyCO2 program. The Jupyter Notebook reads the user input file to see if there are optional parameters that can be used to calculate carbonate variables. If so, the user will be alerted and are offered the option to also include those variables. The notebook provides an easy way for users with varying degrees of expertise to have fine-grained control to calculate carbonate variables by either accepting the default options or by refining various parameters. The new variables created are appended to the merged input file, and a new CSV called output is created. This is the file which will be used in the next step, appending sea ice surface concentrations. Users are able to choose sea ice concentration products produced from two different sources, the Canadian Ice Service and Bremen University, based on their requirements. For example, the Canadian Ice Service data is more accurate for coastal areas, while the Bremen University data produced from AMSR-2 satellite imagery is more appropriate for open ocean analysis. Raster images from the University of Bremen are downloaded based on the sample dates provided in the output CSV that was used as the input. The Canadian Ice Surface files are only provided in weekly intervals, so the closest week is chosen. As Canadian Ice Service files are provided as shapefiles, the shapefiles are downloaded and then converted to raster images. Sea ice concentration values at the sample sites are extracted and appended as an additional column in the input dataset. The file is also converted to a shapefile and overlaid on a map in the right-hand side of the notebook. Through this process, users are able to download the following data files for further analysis: raster images of sea ice concentration from the University of Bremen, shapefiles of sea ice concentration from the Canadian Ice Service, a new data product of the raster images of sea ice concentration from the Canadian Ice Surface, a new data product of the CSV output data file with sea ice concentrations appended, as you can see here, and that same CSV output file converted to a shapefile. Our next step is to integrate the Sentinel Hub visualization platform to allow users to overlay their geospatial locations on top of the same raster image used to extract the sea ice concentration values. I would like to thank all my partners and collaborators on this project, and thank you for your attention.